In the last class, we discussed about a necessary and sufficient condition for the existence of perfect matching in bipartite graphs. So, that condition was called the Hall's condition, and it was about we told the Hall's condition was if every subset of the A side has neighborhood, the cardinality of the neighborhood at least as much as the cardinality of the set itself, then the Hall's condition was satisfied. And then we told if this Hall's condition is satisfied, then there is a bipartite matching in this graph, and vice versa. For instance, if there is a bipartite matching in the graph, then it is clear that there is this Hall's condition will be satisfied, because you take any subset, then this matching will get neighbors for that. For instance, if you had this subset, this perfect matching will take each vertex of it to a distinct neighbor, and together the neighborhood has to be at least as much as the neighborhood of the cardinality of S. Therefore, it is a necessary and sufficient condition. In other words, if a perfect matching is there in the graph, in the bipartite graph, then the Hall's condition will be satisfied. If the perfect matching is not there, it will not be satisfied. In other words, if it is satisfied, there will always be a perfect matching. Now, we will look at general graphs. This was only about bipartite graphs. So, what about a necessary and sufficient condition for the existence of a perfect matching? One factor. Perfect matching, as we already mentioned, another word for perfect matching is one factor. We are interested in some necessary and sufficient condition for the existence of a one factor in a general graph, general undirected graph. So, this famous condition called Tutte's condition is a necessary and sufficient condition for that. What is that condition? Let G be a graph. It need not be a bipartite graph now, as I told. Now, we say Q of G is the number of odd components in G. What do I mean by odd components? So, let us take a graph. So, the graph can be, say, you can consider this graph. So, you can consider this graph together, this together is a graph. So, now this graph consists of 1, 2, 3, 4 connected components. Some of the connected components, some connected components have even number of nodes in them, some connected components have odd number of nodes in them. For instance, this is a 1, 2, 3, 4, 5. So, it is an odd component. This is an odd component, this one. Why? Because it has an odd number of vertices in it, but this is an even component. So, let us say I can mark it with another color. This is an even component. This is an even component. What about this one? This is also an even component because it has 4 nodes in it, an even number of this thing. On the other hand, this is an odd component again. So, the odd number of odd components in this graph is 2. So, we write Q of G is equal to 2. So, this is the notation for that. Sorry, I can write it. So, the Q of G equal to 2 is what we write for this graph. So, we do not have any notation for the number of even components or the total number of components, because we need only the odd components. So, Q of G means the number of odd components of the graph. So, now we consider some subset S of the vertex set, and consider that we remove that subset S from G and count the number of odd components. This is Q of G minus S. G minus S is the graph which remains after the removal of the vertex set S, right. When you remove the vertex set S, remember you remove all the edges incident on those vertices removed also. So, essentially you will get the induced subgraph on V minus S, right. So, the number of odd components you consider in that, and for the Tutte's condition to be true, we need the number of odd components to be less than equal to the number of vertices removed, the cardinality of the set we removed. So, we can probably consider an example. So, one possibility is we can look at an example here. So, here I draw this kind of a graph, 1, we can consider this graph for instance. So, here let us consider this vertex set, say let us say this vertex set. Let me call this singleton set, this one point vertex as S. So, what happens if I remove this S? Of course, if when I remove this S, all these edges will go away. Now, the remaining graph, that is G minus S, the remaining graph is G minus S. What will be that? So, I will mark it like this, say so, this is the remaining graph. So, let me remove it and place it. Okay. So, the remaining graph, so I can say mark with another color here. So, this is the remaining graph. So, what is coming inside the green is the remaining graph. So, this graph, how many odd components it has? This is one odd component because there is only one vertex. This is another odd component because only 3 vertices here. This is another one, third, and then here is, this is not an odd sorry, this is also an odd component, 1, 2, 3, 4, but this is not an odd component. This is not an odd component. 1, 2, 3, 4, 4 odd components we have. So, we have Q of G minus S is equal to 4 here. So, we can take maybe slightly different example, say so another one. So, let us say this graph. Say consider this 2 elements subset S. Now, this is S now. Suppose I remove this set. So, what all things will go away? This edge will go away, this edge will go away, this will go away, this will go away, and this also will go away. So, what we get, the remaining thing what we get is this one and this one. So, this is the G minus S, and sorry, this also, and this is one even component, this is another even component, but this is an odd component. So, here Q minus G minus S, Q of G minus S is in fact 1. So, this is what the number of odd components means. Now, Tutte's condition says for any subset S of the vertex set of G, when we remove the vertex set S from the graph, the number of odd components has to be less than equal to the cardinality of S itself, less than equal to the number of vertices we removed itself. That is what Tutte condition says. So, it the Tutte's theorem says that the Tutte's condition is a necessary and sufficient condition for the existence of a perfect matching in G. That means, G will have a perfect matching if and only if Tutte's condition is satisfied. Let us say one side is very easy. For instance, if you want to check that the Tutte's condition will be satisfied if a perfect matching is present in G, how will we proceed? So, this is the way. Let us say, suppose let us consider a graph and we have a perfect matching, and then you picked up some subset S. So, some subset S, there are some vertices in it, and now these are some of the odd components of this. These are the odd components of this. There can be some even components also. It is possible that there are some even components. This is even, this is even, this is even, like that, and these are all odd components. Odd components. Okay. Now, you see, if there is a perfect matching, here this perfect matching will be matching things like this, but it is clear that at least one vertex will remain here unmatched. That means that there is at least one vertex in this component that does not get a partner with respect to the matching we are considering from the same component. Therefore, where should its partner be? Its partner has to be here, somewhere in S, right, in S, because there are no edges across. Here there is no edge, here there is no edge, here there is no edge. Therefore, its partner, the partner of this vertex cannot come from this or any of this, because they are not adjacent. So, its partner has to come from this thing, because if it is a perfect matching, every vertex has to be matched. Now, what about this odd component? Same thing is true. After however, in whatever way the vertices are matched here, there should be one vertex here which does not get a partner here, because the total is odd. Everything cannot get matched in that. So, its partner should come from this side, and this cannot be this, it should be different, right. Now, similarly from this also, it should get a partner from this. So, every odd component should get a partner from this thing. Clearly, there should be sufficient number of vertices in this to provide partners for all of them, which means that cardinality of S has to be greater than or equal to Q of G minus S, because there are so many components. Cardinality of S should be greater than Q of G minus S. So, let us that is what we know. So, the one side of it is very easy. That means, if there is a perfect matching, the Tutte's condition has to be satisfied. For every subset S, the number of odd components of G minus S has to be less than equal to the cardinality of S itself. The other side is more difficult. Other side means you want to show that if there is no perfect matching in a graph, it is essentially because the Tutte's condition is violated. That means, the Tutte's condition is always violated whenever there is no perfect matching. So, if there is no perfect matching, we should be able to find some subset S such that the number of odd components of G minus S is strictly greater than the cardinality of S. That is what we will need, right. So, such a set is called a bad set. That means, a set S for which the Tutte's condition gets violated. That means, a set S for which Q of G minus S, the number of odd components of G minus S, is strictly greater than the cardinality of S, is called a bad set. We will call it a bad set, and essentially we are saying that if there is no perfect matching in the graph, there should be a bad set, or in other words, if there is no bad set in the graph, there should be a perfect matching. So, how do we show that this is true, right? So, to show this thing, we proceed like this. So, our intention is to show that whenever there is no perfect matching in G, then there is a bad set. So, take a graph G, whichever graph you like, such that it does not have a perfect matching. We have to demonstrate a bad set, show a bad set in this thing. To show this bad set, so instead of directly showing it, we will use some tricks. The first observation is, so we need not really show it in G itself, we can add some edge. For instance, if there is a some two vertices u and v in G such that u is not adjacent to v, then we could have added this new edge to G and made it G plus E, and then we could have demonstrated a bad set in that. If we somehow manage to get a bad set in G plus E, then that bad set will be a bad set in G also. Why is it so? So, let us say, so we have this graph G. What I am saying is, if there is any vertices u v, so this is called u. So, you can try adding this new edge to it. So, we will get this new graph will be, say, G1 we can call it. So, this is G plus E, right, G plus E. So, I am saying it is enough to demonstrate a bad set in G plus E, that same bad set will be a bad set for G also. So, is it obvious? Suppose, say, this is a bad set for G plus E, yes. So, that means we have several, we look at the odd components of G plus E, these are the odd components. There can be some even components also, do not worry about it, this is even, this is odd. This number of odd components is by definition, because it is a bad set. So, G of G dash minus G1 G1 minus S, G1 is what we call it, right. G1 minus S is strictly greater than the cardinality of S, that is why it is a bad set. Now, we consider the corresponding set S in G. Is it a bad set in G also? So, it depends on where this extra edge E is. So, in G, with respect to G, we can think where was that edge, newly added edge occurred. For instance, if that newly added edge was like this, both n vertices inside S, then the picture is not going to change for G also, because the cardinality of S is not going to change, neither the number of odd components is going to change. So, therefore, this inequality will be still true in G. Similarly, for instance, if the bad set was the edge was like this, the edge was like this. If the edge was like this, then again we can see that S, the cardinality of S is anyway not going to change, because it is the same vertex set, only putting an edge is not going to change anything, or removing an edge is not going to change the cardinality of S. Neither is it going to change the number of odd components, right. So, therefore, even if the edge is from S to some component, it is not going to change the inequality, it is going to be the same. Okay. The next situation is, suppose the edge was something like this, sorry, not like that. So, because it is in this picture is about G dash. So, suppose, because the edge can be now inside this, right, inside this. So, now we, when we get rid of the edge, to go back to G, this is G dash, what can happen? See, if nothing happens, if this component remains intact as such, connected even after removal of this edge, then it's fine. Again this inequality will be satisfied, and therefore S will be a bad set. But it's possible that when we remove this edge, the it may so happen that this may get cut into two pieces because of this edge only they got connected. So now if by chance this was an odd component, both of them happens to be an even component, then we will lose one odd component from the total, right, and this happens to be just one more than S, then this may be violated. So then we will not be able to claim that S is a bad set in G. But luckily that situation will never occur, because it is not possible for both of these things to be even. Why? Because both of them are even, this together also should be even, number should be even. So that will not be an odd component in the first place. So therefore one of them has to be an odd component. So for the destroyed odd component, we will definitely get one or smaller odd component. So the total number of odd components will be equal or more. It is possible that both of them are odd component here, then it may increase. So this S will still remain as a bad component, because this inequality will be satisfied in all the cases. So what I have now shown is, somehow if we add an edge to G and ask whether there is a bad set in G plus E, and if the answer happens to be yes, then the answer to the question whether there is a bad set in G is also yes, because the same bad set which works for G plus E is a bad set for G also. But what is the good thing about it? So you are asking, instead of looking for a bad set in G, you are looking for a bad set in G plus E. Does it make the problem any easier? So the interesting thing is, okay, if you can look at G plus E for a bad set, you could have looked at G plus say one more edge, E plus another edge, right, for instance. So let us say we could have told, so I will first start with G, I will add an edge to G and make G1. I could have looked at this thing, but instead of looking at that, I could have even added another edge E2, and then could have created a new graph with more number of edges G2, and definitely I could have added one more edge E3, and we could have made a G3, and then we could have looked at this thing. Anytime if I get a bad set, that bad set will be, the bad set here will be a bad set here, bad set, that same bad set will be a bad set here, and it will be a bad set here. It would be enough to look for this thing. And finally you could have come to a graph which I call G dash, such that no more new edges can be added without creating a perfect matching. So of course it is true that if you keep on adding edges, and if you somehow get a bad set in any of these graphs which is created by adding more edges, then original graph also has. So our aim is to keep on adding edges till a point that it gets saturated in some sense. What do we mean by saturated in some sense? That means we cannot add any more edge without violating some property. What is the property we are interested in? Because G was a graph without a perfect matching. That is the property we are interested in. When we are adding new edges, we will make sure that these new graphs are also without a perfect matching. So in other words, when a new edge is added, if a perfect matching comes in the graph, then we will not add that edge. We will look for another edge that can be added. And then G dash is such that we don't see any more new edges which can be added to G dash without introducing a perfect matching it. In that sense, we say that G dash is an edge maximal. This is the word, edge maximal. Edge maximal graph. Edge maximal graph in what sense? Edge maximal graph with respect to the property of not having a perfect matching. That's what. So you can tell about a graph that it is an edge maximal graph. It can be with respect to any several property, some property, but here the property we are interested in is the absence of a perfect matching. So again, to repeat, what we are interested in is to prove that if there is no perfect matching in a graph, then there is a bad set in it. Now, instead of directly looking for a bad set in G, we will keep on adding edges to G and look for a bad set in the corresponding edge maximal graph G dash, and this edge maximal with respect to the property that there is no perfect matching, and also it is made from G by adding more and more edges. The good thing is, if you somehow get a bad set in G dash, the same bad set will be valid for G also. That is what we argued, right. So, then we can as well look for a bad set in G dash. So, what is good about G dash? Why should we go to G dash and look for a bad set? The good thing is about G dash is that it is some kind of a saturated graph, it is edge maximal. In other words, if you add any new edge to it which is not already existing in it, then a perfect matching will evolve. What can I tell about the maximum matching of such a graph? Of course, it's almost there in the sense that it is n by 2 minus 1. In other words, so if this is an edge maximal graph G dash, this is the edge maximal graph G dash, and you just add an edge, suppose say you decide to add this edge, then immediately you can see that there is a perfect matching comes, which means that there was already some matching which was just one less than a perfect matching. That means every other vertex was matched by something. These were the only two vertices which are unmatched, and then this also added. So, there is a perfect matching. So, this is true for every non-adjacent pair. Any non-adjacent pair will be such that they are the only two unmatched vertices for some matching, right. So, this is a good property, this is going to be useful, that is why we are looking at this edge maximal graph. Now, how am I going to prove the result for this? Now, we are looking for a bad set in the edge maximal graph, but when we are looking for a bad set, what is a bad set? Bad set means the number of odd components of G minus S, the number of odd components of the graph generated by removing that vertex at S is strictly less than the cardinality of, strictly greater than the cardinality of the number of the set of vertices removed, right, if that is the bad set. But then this is a difficult property. How do we find out such a set even in an edge maximal graph, even with the property? So, what we make this edge, so what kind of set it will be? That is what we should first think. For instance, if there is a bad set in an edge maximal graph, how will it look different? Can we tell something about it? So, therefore, let us think about what kind of properties a bad set, if at all it exists, will have in an edge maximal graph. So, suppose this is a bad set. I am not saying that it exists in an edge maximal, suppose it exists, then it should be like this. So, see, these are the components of the edge maximal. So, these are the components of G minus S. Let me call it C1, C2, C3, C4 like that, right. So, now, so the question is it possible that there is a pair of vertices in this such that they are non-adjacent, U, V. Is it possible to have a U and V in this thing such that they do not have any connection between them? So, you can easily see that it is not possible, because if what would happen, suppose this is assumed to be a bad set. That means, suppose these are the odd components of this, some even components are there, the number of odd components is going to be bigger than this, right. Now, suppose if I add this edge in this thing, what will happen? Then we know that already after adding this edge there is a perfect matching. If there is a perfect matching, you cannot have a bad set, but then this is going to be still a bad set because the number of odd components is going to remain same by adding this edge, and then the cardinality of this is also going to remain same. This bad set will remain as a bad set. So, there is no way of producing a perfect matching in this graph by adding a new edge here within this thing, because any new edge added here will not reduce the number of odd components. So, what does it mean? Because it is an edge maximal graph, if there were two vertices inside it which were non-adjacent, we should be able to add a new edge there, and then perfect matching should come. So, we can only infer that. So, this should be complete graph, this should be complete graph, S should be a complete graph. And what about each of the components? The same argument is true, because if there is a non-adjacent pair, we can add that edge, we will get a perfect matching. Then if there is a perfect matching, you cannot have a bad set, but this bad set remains as a bad set because the number of odd components hasn't changed, number of vertices in the set hasn't changed. So, if it was originally a bad set, it has to be a bad set. So, all these things has to be, this should be a complete graph, and this also should be a complete graph, and similarly this is also a complete graph, yeah, this is also a complete graph. So, this similarly this, all these things are complete graphs, that is what we see. Now, what about a connection between these, say for instance these connections? Can I tell anything about them? Is it possible to have a missing edge here? That means some edge, some vertex here and some vertex here. Is it possible to have have them non-adjacent? In that case, the same argument again tells us it is not possible, because if I put this edge, again the number of odd components is not going to change. This is again an odd component, this is an odd component, this is an odd component, because the numbers haven't changed. And similarly, the vertex, the cardinality of this vertex set is not going to change. So, this is going to be a bad set again, right? This is going to be a bad set again. So, it is not possible. So, what we say is that it is not possible to have a non-adjacent pair here. In other words, all the edges across should be present, right? Because even if one non-adjacent pair was there, I could have added that edge, argued that a perfect matching came because of that, and because the perfect matching is there, then my graph cannot have a bad set. In particular, this particular set cannot be a bad set, but it is not true. It remains a bad set. So, what we can infer is every connection between this, etc., should be present. So, for instance, if I again mark it, what I can see is all the connections between these things, between these things, between these things, between these things should be present. The graph should be like this. With respect to the bad set, we should see something like this. What I have now told is essentially about the general. So, if at all there is a bad set, it should look like this. It should have this special structure, but I have not told that there is a bad set. I have not also told that any suppose I am interested to find a bad set, and the other question. So, this is how the bad set should look. The bad set will look, but then is it also true that suppose I get some set like this? This is, it looks like it is much easier to figure out this, whether this kind of a set is present or not, right? So, suppose if I find such a this kind of a set in the graph, can I be sure that this is going to be a bad set? Up to now I have not proved that, but it is a valid question to ask, because the bad sets have a nice structure like this. So, I can also ask the reverse question, that suppose I see a set with this special structure, that is always going to be a bad set. It so happens that it is going to be a bad set. Why? Because we know that in the perfect matching, in the edge maximal graph we do not have a perfect matching. And suppose I find a set like this, and if it is not a bad set, then it should have q of g minus s less than equal to cardinality of s. That means the number of odd components has to be, so let us say these are the number of odd components, right. I have marked the odd components like this. So, this odd components has to be strictly less than equal to the cardinality of s. Now, I say that this is a contradiction to the assumption that we do not have a perfect matching in the graph, because we can always match all the vertices of the even components, because it is a complete graph, and like they can be paired off perfectly well and perfectly, and then here also the odd components can be paired off except for one vertex. Here say this vertex I can assign a partner from here, right. Similarly, here also all the vertices can be paired off except that I can one vertex will be left, but it can get a partner from here, another vertex other than this. Similarly, here also I can pair off all the things, but one vertex will remain, that can get a partner from here. So, from each of them. So, I will, because the number of odd components here is strictly less than equal to the cardinality of this thing, I will be able to assign one for each odd component, one vertex from the set to each for each odd component, so that it can provide a partner for the left out vertex of the odd component. So, we will get a perfect matching in G. So, our assumption that this graph edge maximal graph G dash did not have a perfect matching was wrong. They did not have a perfect matching was wrong. So, what we see is not only that the bad set has that special structure, that means a clique, it is a clique and all the components are cliques, and between the component and we have complete connection. Not only that, if we get any set with that particular structure, that special structure, it has to be a bad set. This also we see, right. So, then you can see that. So, okay, there was one point I missed. So, for instance, one can see how what if this cardinality of this was more than the q of main. So, what if why do I think that the remaining vertices here can be paired off? Will it be even? If it is even, you can always pair off. That is true, because if the number of vertices of the graph is odd, then we know that the set phi can be taken as a bad set, because if you consider the cardinality of phi, and this is always equal to 0, and this is going to be less than 1, which is the cardinality of the odd component, the odd graph. If it is a connected graph, there is one component that is odd. So, but then if it is a disconnected graph, at least one component has to be odd. So, this q of g minus s is going to be greater than or equal to 1, and that is greater than the cardinality of phi. Therefore, for odd graphs, this statement is trivially true, because you can always take phi as the empty set as the bad set. So, we can assume that it is an even graph. So, therefore, we can see that after pairing of the vertices by some matching, we have removed already. So, we have already considered even number of vertices. So, whatever is left out has to be an even number, because the total is even. So, the remaining even number of vertices also can be paired off. That is why that can be completely paired off. So, this we have already argued that any bad set has to look like that particular special structure, and also if any set has that special structure, then it has to be a bad set. So, you can see that there is a interesting thing here, that means we have started to find out a bad set in G dash. Now, we do not have to look for the bad set, which is more difficult to find out. We only have to find out a subset of G dash which will give which has that special structure. That means it induces a clique, all the components induces a clique, and between each a component and the set we have the complete connection. That may be much easier to find out. Suppose I want to find out such a set, what will I do? Okay, so because the vertices in S has to connect to every other vertices in the graph. Can you see that? For instance, you take a vertex here, you can see it is connected not only it's connected not only to the vertices inside this, it's also connected to all the vertices in the component, this component, this component, this component, every vertex. In other words, such vertices are usually called universal vertices. So this is the word universal. Such vertices are called universal vertices. A vertex which is adjacent to every other vertex in the graph is a universal vertex. And you can see that if such a set exists, all the vertices in that set is going to be a universal vertex. So it is very natural to collect all the universal vertices in the graph. If you want to get such a set, that is the most natural approach. And if once we collect all the universal vertices, then we will get this S as the set of universal vertices. So naturally, because it is universal vertices, this complete connection will be there. Now you look at the components of which results by removing this thing, and naturally, because these are all universal vertices, all these connections will be there. So that particular structure will be there already, right? So all these connections will be there. So now what is missing? So have you already got whatever we are looking for? So it is like this. We will have all these connections here. We will have already got this much. We have all these connections here. We have all these connections. So we have this complete connection inside also. This much we got. What is missing is this. Probably there are two vertices here which are non-adjacent. In other words, probably this thing inside this component we may not have the complete connection. Probably within this thing we may not have the complete connection. Something like that. So we almost got it, but still there is a problem. This doesn't have the kind of structure we are looking for. So you may ask, what happens if I didn't find any universal vertices in the graph? In that case, this has to be an empty set. So it's trivially true, this much has happened. So the components of the graph itself will be the thing, but then there won't be any vertex in the graph which is connected to everything else. So let us say if there is a contradiction, that is if there is a situation that some component, say let us say this is Ci, this component has two vertices such that they are non-adjacent. We are going to produce a counter example, contradiction based on that. Why? How are we going to do that? So contradiction to what? So you remember this was an edge maximal graph, but it didn't have a perfect matching, edge maximal without a perfect matching. So we will show that if there is an edge missing in this component, we will have a perfect matching. This is what the contradiction here. It may look a little surprising when we are saying that when there is an edge is missing here, we are going to show that there is a perfect matching, which will be a contradiction because there is no perfect matching. How are we going to do this thing? So we will now, we don't need that picture. Let's look at this graph. So if we have a missing edge, so what is the possibility? So you see, one thing is, see, you know that if you add this edge, you will get a perfect matching. That's the property of the edge maximality. So therefore there is already got a matching of this graph which matches of every other vertex of the graph, so except these two vertices, let us say called u and v. So these are the only two vertices which are unmatched with respect to that matching. So is it possible to augment this matching? Augment means, can you somehow increase the cardinality of the matching? If you manage to increase even by 1, we are done, because it is already n by 2 minus 1, it will become n by 2. That means it will be a perfect matching. So you can make an attempt. For instance, you can start, so one, as we studied in the bipartite guide, one method is to find out an augmenting path. Augmenting path means you start with an unmatched vertex, follow an unmatched edge, and then matching edge, then unmatched edge, and then matching edge, and then finally if you manage to reach the other unmatched vertices, then it is an augmenting path. What you can do is you can replace the edges which appear in that path from the matching by the edges which appear in that path from outside the matching, right. So, you swap the matching edges with the unmatched edges, right. So, is it definitely you can go out of, for instance, if I start my path from U, you can always go from U to some vertex. So, definitely that vertex, because it is not this is not adjacent to it, and I can always follow this red edge now, this red edge now. Now, from here I can try to find another vertex, maybe I reached here. So, after some time, so what is the guarantee that, so I will not, so all my, so I keep going and then I reached here, and then what is the guarantee that when I look for neighbors of these things, so that I can continue my path, so I will not end up with the already seen vertices. This is something you have to try. So, if you try for some time, you will realize it is a little difficult to show that if you can continue that path until you reach the other unmatched vertices. So, here is a trick, a very nice trick, so which allows us to complete, to go forward. So, what is the trick? So, the trick is, suppose you have, this is the graph, instead of one non-adjacent pair of vertices, you have two non-adjacent pairs of it. Let me call xy and uv. Now, so I may want to start at x. So, let us say if I put the edge xy, then you will get a perfect matching here. I will call it a red perfect matching. This corresponds to the xy, because it will match of all the vertices. In particular, there will be an edge like this also, that will be also matched. So, everything will be matched, right, by red matching, but only the two vertices are unmatched by the unmatched vertices with respect to this red matching, that is x and y. You know, similarly, if you try to put this uv vertex, right, so uv edge here, then also we will get a matching. Let us say it is a green matching, and then green matching will be matching every vertex also similarly somehow. So, here also in particular there will be this matching, some green matching will be there. Every vertex will be matched except u and v here. With respect to the red matching, only x and y were not matched. With respect to the green matching, u and v are matched, unmatched. Now, what is the good thing about this? So, the good thing about it, for instance, if I start traveling from x and I am trying to reach the vertex y. So, one easy way is to take, because this is only here I see only a green edge, the red edge is not there because x is unmatched with respect to the red matching, but definitely when I reach here I will see a red edge on that, because that has both red and green there. So, a green is coming in, then you have to see a red also. When I reach here, definitely I will see a green here, because this vertex has both green and red. Via red we entered, then I should be able to exit through a green. Similarly, here also I will be able to do the same trick, right. By a red I can follow. So, I can keep on going. You can see that we will never come back to an already visited. For instance, this path is never going to come back to an already visited vertex, because it has only one red edge incident on it and one green edge incident on it. Both of them are already used. If some via red edge again it has to come, or via green or red edge if again it has to enter, it will violate the property that there is only one green and one red edge adjacent to that vertex, right. So, therefore, that will never happen. So, the earlier problem that that question, what if it again comes back and hits the vertex which is already visited, will not happen here. But then are we reaching the destination that means starting from x can we reach y, that is not guaranteed, because this can stop at 3 points. If it stops at y, well and good, we got an augmenting path. But so what will you do? Suppose if you reach y, then naturally we will somehow be entering y with a green edge, right. In that case we will replace all the red edges in path with green edges. We clearly see that because you start with the green and end with the green edge, the number of green edges is one more than the number of red edges, and therefore the number of edges in the matching will increase. In other words, we are augmenting the red matching by replacing some of the red edges by green edges. But this will not happen, or in other words, you can see that in that case this both x and y will get matched, all other vertices also will get matched, right. But what if it never reaches y? So where else it can go? It can go and end in u or v. If it is ending in u or v, it is ending with a red edge, see, because there is no green edge there. So there this it is not an augmenting path, it is just an alternating path starting with green, then red, green, red, and it is ending with red. So both red edges and green edges in such a path will be equal. By switching the red with green is not going to increase the length of the cardinality of the red matching or with the green matching. So the only solution that, so you can think for some time whether you can somehow solve this issue, but it doesn't look like there is an immediate solution for that. So the only thing is to have, we can think wishfully, what if I have two edges here, like say suppose I have an edge here and an edge here. So definitely these two edges are not going to be of red color, because this red edge is not going to be incident with y. So this has to be of a different, I mean it won't be red, right. Similarly, this cannot be a green edge because there is no green on this, right. So it has to be some other color, neither red nor green. So similarly this one, suppose there are two edges, whichever, this won't be green or red, whatever, if at all they are, then we don't have this problem, because when we reach this via a red edge, we can follow via this, and for the time being we can assume that this is a green edge, or in other words we can replace all the red edges in it by these green edges as well as finally this one. So that will be an augmenting path, though it is not fully green, red, it is a green, red, finally red, and this new edge. This is as good as green, because we are only planning to replace all the red edges by a different kind of edges. We augmented the red matching, right. So that can happen. So but then there is no guarantee that this kind of a structure may exist. So how do we make sure that we can pick up two non-adjacent vertices from the graph such that this kind of a structure comes? So this is what we want. So two vertices x and y, u and v, such that, so this is non-adjacent pair, this is non-adjacent pair, but we need this thing. So this is the trick finally. To do this thing, we know that by our earlier picture, we know that, so this was our picture. So we have all these connections, there is all this inside, but there is at least one component, say, which we call Ci, such that two vertices, there are these non-adjacent two vertices here. So I will just take this component, because it is a component and this is two non-adjacent vertices in it, there should be a path starting from here to here somehow and reaching here, right. There should be a path. So we can consider that path. Let us say this is the two vertices, let me call it x and y, let me call it a and b, let me call it a and, let me call it a and b, and then this is non-adjacent. There is a path inside that component which goes from a to b. So let us consider the second vertices of this thing, this path. So, this A will be called x and let us call this y. Clearly, there is no connection between this and this. See, this path I will take as a shortest path. If it is the shortest path, you can clearly see that this edge cannot be there. What if this edge is there, then we are going to get a shorter path here like this, right, than this one. Then this path, this path is going to be shorter, right. So, therefore, we are not going to have that edge here. Now, what we have is an a B, but if I take the shortest path in it and this third vertex, this is A is the first vertex, second vertex, and this is the third vertex, and call this as x, this as y, and this is non-adjacent pair, and both of them are in the component and it does not matter for us. Now, we will consider, because this connection, so let it be u. Now, if I can find one other vertex v such that v is not adjacent to u, then we are done, because then we get a xy here, a uv here, right, and this connection is there. This is the kind of connection we were looking for, right. So, two non-adjacent vertices xy, uv, and then u is connected to both x and y. But then how am I sure that this will be there? Because u is from the component Ci, and therefore, it is not in S. U does not belong to S. So, it is not a universal vertex, because we have collected all the universal vertices in S. So, there should be at least one vertex in the graph which is non-adjacent to U, that will be V, and definitely it is not x or y, because these things are connected to U. So, we get this pair. So, we can find an augmenting path for this the matchings which are produced based on xy and uv, and then we will get a bigger matching, that will be a perfect matching, that will contradict the fact that there was no perfect matching in the given edge maximal graph. This will be a contradiction. So, this completes the proof. This is what guarantees us that if we collect all the universal vertices, that will have the kind of special structure we were looking for, and that is going to be a bad set by our argument. In the next class, we will summarize the key points of this proof once again.